History of Vector Analysis, Episode 11, Tate and Quaternions. You are here. Hey, it's old Doc Oler. Welcome back. Today is Biography Day. We are primarily going to discuss the life and times of one Peter Guthrie Tait. You have probably never heard of him, but he was near the center of the scientific and mathematical world in the mid-1800s. He went to elementary school in Scotland with James Clerk Maxwell, and they became lifelong friends. He also co-authored one of the most influential science books of the entire 19th century with William Thompson, Lord Kelvin. Thompson is arguably an even more important figure than Maxwell. And, key to our story, early in Tait's professional career, he began a correspondence with William Rowan Hamilton near the end of his career, but still one of the biggest names in mathematics at the time. Tait came to not only learn about quaternions from Hamilton, but went on to develop their practical side to the point where they could be applied to some of the new sciences that were arising, including electricity and magnetism. The book he wrote on the subject, an elementary treatise on quaternions, was well organized and, at least to an extent, comprehensible, characteristics that did not apply to Hamilton's lectures on quaternions. It was through this book that he introduced his friend Maxwell to quaternions, and it was this book that was used a generation later by two guys who we'll meet in future episodes, Oliver Heaviside and Josiah Willard Gibbs, to create/extract modern vector analysis. Meanwhile, Tait's on and off again partner, William Thompson, led the charge against the adoption of quaternions, and in fact of all vectorial systems. Okay, so Tait is in the center of all this, yet he is best known today, in those circles in which he is known at all, for his work in thermodynamics. Personally, I think Tait calls out to have a Broadway musical written about him, but hey, that's just me. Peter Guthrie Tait was born in 1831 in the small Scots town of Dalkeith to a middle-class family, and then was sent off to the prestigious Edinburgh Academy starting in 1841 at the age of 10. It was there that he met and became lifelong friends with his fellow Scot, James Clerk Maxwell. He went on to attend Cambridge, where he graduated as Senior Wrangler, the one with the highest score on the legendary Cambridge Mathematical Tripos exam in 1852. Maxwell himself would finish as merely Second Wrangler 2 years later. This award, originally secretive, was first given in 1748 and continues to this day, although its importance has been downplayed some in the past century or so to reduce the number of suicides that studying for it seemed to induce. After Cambridge, in 1854, Tait was named Professor of Mathematics at Queen's College in Belfast, Ireland. Then in 1860, he was chosen as the Chair of Natural Philosophy at Edinburgh University back in Scotland, over Maxwell. He remained there until his death in 1901. From 1855 until its publication in 1867, Tait collaborated on the two-volume book Treatise on Natural Philosophy with William Thompson, who was already famous by that time. While largely unknown today, Treatise was highly influential in its day and is sometimes credited as the book that placed the concept of the conservation of energy, where heat was now included as a form of energy, at the center of physics. This book was commonly known at the time as Thompson and Tait, or as T and T prime. We must discuss William Thompson here, not because he was the senior partner on Tait's book, but because of the role he played in opposing the adoption of quaternions. Thompson was a brilliant Scottish polymath who spent his entire professional career in Glasgow. Thompson was another Cambridge alum and was fully expecting to be the first Wrangler in 1845, 7 years prior to Tait, but like Maxwell later, ended up as Second Wrangler instead. Perhaps it is the Second Wrangler position that should be sought. Anyway, he was a brilliant theoretician, and his work on thermodynamics and classical E&M were and are immensely important. But he was also very practical, and he helped design the first transatlantic cable. This made him rich and famous, and Queen Victoria knighted him for it in 1866, shortly before Thompson and Tait's book appeared. Thompson was made Baron Lord Kelvin in 1892, near the end of his career, and became the first scientist to become a member of the House of Lords, for what that's worth. He was famed as much for his intimidating demeanor as for his brilliance. He is considered today to be in the same intellectual class as Newton, Einstein, and Maxwell. Hamilton, as you may recall, published his unreadable Lectures on Quaternions in 1853. Tate, as a young senior wrangler just out of Cambridge, was one of the few who bought a copy, in part, he stated, simply because he liked the sound of the word quaternion. But he, almost uniquely, became enamored with the subject. Well, the math parts anyway, not so much the metaphysics. Tate wrote to the vastly more senior Hamilton in 1858 during his stint as a junior professor in Ireland, and Hamilton responded. Thus began a lengthy correspondence between the two men that ended only with Hamilton's death 7 years later in 1865. Hamilton quickly recognized Tate as a talented mathematician, one worthy of sharing his thoughts with. Tate started making original contributions to the field, eventually publishing some 70-plus papers on quaternions in his lifetime. Importantly, though, he always kept his quaternion work separate from his other work, even where it would have made sense to incorporate it. This was likely due to the opposition of vectorial methods by his other senior partner, William Thompson. I'll get back to that in a moment. Upon Hamilton's death in 1865, Tate became the quote-unquote heir to quaternions. He published this book, an elementary treatise on quaternions, in 1867. The more influential second edition appeared in 1873. This was the edition that would be offered to Maxwell and studied a generation later by Gibbs and Heaviside. There was also a third edition that appeared in 1890. One of the things that both Hamilton and Tate loved about quaternions was that they could express equations without reference to a specific set of coordinates. As noted, as much as Thompson was taken with quaternions, his senior partner, William Thompson, was not. Thompson, like most mathematicians and physicists at the time, did his 3D math in quote-unquote Cartesian form. This implies that there are three distinct equations, or more if there's cross terms, for the three spatial dimensions x, y, and z, or perhaps r, theta, and phi. I'll show some examples in the near future, but it is worth acknowledging Thompson's point that most of the time, to solve an assigned or real-world problem, you have to assign a coordinate frame anyway. My historian guy, Michael J. Crow, argues that Thompson's fierce reputation and his unambiguous opposition to quaternions probably slowed their acceptance by the community. Crow further argues that Thompson's, or here's the quote, Kelvin's strong opposition to quaternions probably extended to any sort of vector analysis. That is, Thompson's opposition wasn't simply to the awkwardness of manipulating 4D objects. It was that even if they were only 3D, they would still be not much more than a notational shorthand that would have to be abandoned as soon as you started calculating. To give you an idea of Lord Kelvin's views directly, here is a quote from a private letter he wrote in 1892. Quaternions came from Hamilton after his really good work had been done, and though beautifully ingenious, have been an unmixed evil to those who have touched them in any way. This may seem fairly mild by today's standards, but given Lord Kelvin's towering reputation and considering the rigidity of Victorian England, this is a withering blast. Here is another Lord Kelvin quote about 10 years later and shortly after Tate had died, from a letter that Kelvin wrote to the Scottish mathematician George Crystal. We have had a 38 years' war over quaternions. He had been captivated by the originality and extraordinary beauty of Hamilton's genius in this respect, and had accepted, I believe, definitely from Hamilton, to take charge of quaternions after his death, which he has most loyally executed. Times without number I offered to let quaternions into Thompson and Tate if he could only show that in any case our work would be helped by their use. You will see from beginning to end that they were never introduced. Pretty cold. But Tate had had an ace, his lifelong friendship with James Clerk Maxwell. Now, the young Maxwell was as deferential to the senior Lord Kelvin as everyone else, and his famous papers on electricity and magnetism that appeared in the 1850s and 60s were worked out exclusively in the standard notation of the day favored by Thompson, Cartesian coordinates. However, Maxwell recognized that, in particular, Hamilton's del operator had the potential to illustrate his physical as well as his mathematical views on E&M in a powerful way. After Tate had published his treatise, he wrote to Maxwell, noting that his book elaborated on this del operator and that Maxwell might find it interesting and possibly helpful. In the episode after next, we will meet the legendary Maxwell. But since Tate's book on Quaternions was so seminal to Maxwell and to the development of our modern form of E&M, I want to spend the next episode discussing a little bit about what was actually in the book. Kelvin referred to Quaternions as an unmixed evil. It is my hope that the next episode will give you a chance to see for yourself. Okay, that's it then for this episode. See you next time.